Hi everyone, welcome back to Can Help ASAP. Now that you know the trends in the periodic table, let's use them to work some problems. Our first problem wants us to classify bonds as either ionic, polar covalent, or non-polar covalent. So we are going to have to calculate the difference in electronegativities, or delta chi. We will use the values given in our table. Let's start with part A, carbon-oxygen bond. So delta chi is going to be 3.5 minus 2.5. That gives us a difference of 1. And when delta chi is between 0.4 and 2.0, we have a polar covalent bond. Let's look at the sulfur-selenium bond. Delta chi is 2.5 for sulfur. Selenium is 2.4. We have a difference of 0.1. We know that if delta chi is less than 0.4, we have a nonpolar covalent bond. Hydrogen and fluorine. Delta chi is 4.0 minus 2.1, which is 1.9. So again, we have a polar covalent bond. Now that we have classified our three bonds, the question also asks us, of the covalent bonds, which is the most polar and which is the least polar? Well, the least polar is obviously going to be our nonpolar covalent bond. Now, for which is the most, we just need to find which delta chi is larger, and that is going to be our hydrogen-fluorine bond. Problem number 2 asks us to explain why the ionization energy for arsenic is 0.947 megajoules per mole, while the ionization energy of selenium is 0.941 megajoules per mole. So I am going to find arsenic and selenium on the periodic table here. I know that ionization energy ought to increase as we move left to right. However, arsenic and selenium definitely break this trend because selenium's ionization energy is lower than that of arsenic. So why would it be easier for selenium to lose an electron as opposed to arsenic? I'm going to go and take a look at the valence electrons. So arsenic has the 4s orbital, 2 in there, and the 4p orbital, it has 3 electrons. Selenium also has 2 electrons in the 4s orbital, but it has 1 more electron in the 4p orbital. So I'm not seeing anything obvious in terms of removing this electron from arsenic. However, when I look at selenium, if I remove this electron from selenium, I will gain stability by having that p orbital half filled, and I will lose some of that electron repulsion from having these electrons paired. So that makes sense why selenium ought to have a little bit smaller ionization energy than arsenic. We have gained stability here. Last problem. This asks us about an element that has not yet been synthesized, element number 117. Now, my periodic table actually gives it a name, but your periodic table might not give it a name because it has yet to be synthesized in the lab. So the question asks, what group will it belong to? Well, I see it's in group number 17. We call that the halogen. The next part asks about size. Would it be larger or smaller than astatine? Well, I know based on my trends for atomic radius that as I move down the periodic table, size increases. So element number 117 should be larger than astatine. Oh, another size question. Would it be larger or smaller than element 116 here to the left? Well, again, as I'm remembering my trends in atomic radius, I know that as I move left to right across the periodic table, atomic radius decreases. So therefore, element number 117 should be smaller than element 116. Knowing electron configurations and being comfortable thinking about orbitals and working with them is very important when trying to rationalize our periodic trends. You can see how interconnected chemistry is, and hopefully it'll start to come together as a whole for you. Thanks so much for watching.